Hello everyone, welcome to OHM Institute. I am Surendra Reddy, faculty for electrical machines at OHM Institute. In today's lecture, I am going to discuss about previous GATE examination questions from synchronous machines subject. And I am going to discuss about the past 13 years question papers, that is question papers from 2011 to 2023. And in this lecture, I am going to discuss about 1 mark questions and 2 marks questions I will discuss in a separate video. Okay. So synchronous machines, 1 mark questions from 2011 to 2023. And learning previous GATE questions will give complete insights about the subject and we can understand which areas are more important and what level of questions generally asked in GATE examination. Okay, is it theoretical or numerical, and if it is theoretical, how much depth the questions will go. Okay, and numerical questions how far. Okay, so selecting past 10 to 12 years of question papers will give us more understanding the level of questions at which you can expect in GATE examination. Okay, and here I have the first 1 mark question. This is in GATE 2014 examination. Okay, electrical engineering paper, synchronous machines, 1 mark question. And read the question. A star connected 400 volt 50 hertz 4 pole synchronous machine gave the following open circuit and short circuit test results. Okay, the question is about open circuit test and short circuit test. And if you read the problem, here open circuit test data started. Open circuit test, VOC is equal to 400 volt line to line value. Even it was not mentioned, by default given voltage is always line value. Field current is 2.3 ampere. This is open circuit test data. And then we have short circuit test data that will be starting here. Short circuit test current 10 ampere phase current and field current is 1.5 ampere. Now the question is the value of per phase synchronous impedance in ohm. We are asked to calculate per phase synchronous impedance value. Okay, all right. So this is a question from OC and SC test data of a synchronous machine, and we know that by using open circuit test and short circuit test details we can find out synchronous impedance of a machine, synchronous impedance of the machine. What is the formula? Synchronous impedance is always equal to open circuit terminal voltage per phase divided by short circuit armature current per phase. Okay, we have to use phase values only, then only you will get impedance per phase. But important thing is both these values must be measured at same field current. This is the most important point. We have to measure both open circuit voltage and short circuit current at the same field current. But in the given question, open circuit voltage was measured at 2.3 ampere field current, but short circuit current was measured at 1.5 ampere field current. Therefore, what I need to do, I have to convert short circuit current from 1.5 ampere to 2.3 ampere so that I can take the ratio between open circuit voltage by short circuit current. Okay, yes. So if I note down the data, short circuit current is 10 ampere at 1.5 field current. Okay, and we know short circuit characteristics are linear or non-linear. Yes, in a synchronous machine short circuit characteristics are linear and it will be like a straight line passing through origin. We know short circuit characteristics are drawn between short circuited armature current versus field current, and it will be like a straight line passing through origin. And the given data, yes, at 1.5 ampere of field current, what is the amount of armature current flowing? 10 amperes is the armature current. Okay, 10 ampere is the armature current. Suppose if field current increases to 2.3 ampere, what will be the value of armature current is the question. Okay, so if I know this value, I can easily find out synchronous impedance per phase. Okay, as it is like a straight line passing through origin, directly proportional, right? Short circuited armature current and field current both are directly proportional. So therefore, short circuit armature current is directly proportional to field current. So first case armature current divided by second case armature current is equal to IF in the first case divided by IF in the second case. Okay. So what is armature current in the first case? 10 ampere. Armature current in the second case is the answer we need. And field current in the first case 1.5 ampere, but I need the armature current at 2.3 ampere field current. So from this you can find out armature current in the second case. Okay, you must use a calculator. So I am using a normal calculator. You have to use a gate calculator only. Okay, so if I calculate 2.3 divided by 1.5 into 10, so I'm getting 15.33 amperes. So this is the value of short circuited armature current when field current is increased to 2.3 ampere. Now I have short circuited armature current at 2.3 ampere and open circuit voltage is also at 2.3 ampere. So if I continue further, open circuit voltage is equal to 400 volt. This is line value, guys. And it is very clearly mentioned machine is a star connection. As it is a star connection, what will be the phase voltage will be equal to 400 by root 3 voltage per phase. This is measured at a field current of 2.3 ampere. Okay, and what is the short circuited armature current? We just calculated. Short circuited armature current is equal to 15.33 ampere per phase. This is also at a field current of 2.3 ampere. Now open circuit voltage and short circuited current both are available at same field current. Now I can calculate synchronous impedance per phase. What is the formula for synchronous impedance per phase? It is equal to open circuit voltage divided by short circuit current. What is open circuit voltage? 400 divided by root 3 by 15.33. And if you solve it, you will get synchronous impedance per phase. Okay, so 400 by root 3 divided by 15.33. So I am getting 15.06 ohm per phase. This is the synchronous impedance value. Okay, so before solving this question, one should have idea about open circuit characteristics and short circuited characteristics of a synchronous machine. Okay, so using OC and SC curves, we can find out synchronous impedance of the alternator. But the thing is that open circuit voltage and short circuit current both must be measured at the same field current. Okay, so always in the question, if you read the question properly, both were not given at the same field current. So I converted short circuited current to the required value. Okay, because short circuited characteristics are linear, you can use them. Okay. Okay, so let's move to the next question. This is GATE 2014 examination question, 1 mark question in synchronous machines. Read the problem. In a synchronous machine, hunting is predominantly damped by which of the following? Mechanical losses in the rotor, iron losses in the rotor, copper losses in the stator, copper losses in the rotor. See, the question is about hunting. First of all, we need to understand what exactly mean by hunting and how can we reduce the hunting problem in synchronous machine. Okay, see, hunting is nothing but the rotor swinging nature or rotor swinging whenever load suddenly changes. Okay, so let's see how to understand this. Normally in a synchronous machine, okay, if you consider stator is a stationary element, stator is always stationary, and stator will have a three-phase armature winding, and three-phase armature winding is carrying a balanced three-phase AC current. Yes, whenever distributed winding is carrying AC current through it, it will create a rotating magnetic field. Therefore, stator magnetic field is rotating in nature and it will rotate at a speed known as synchronous speed. Stator field will rotate at a speed known as synchronous speed. What is the formula for synchronous speed? 120 F by P, where F is nothing but stator frequency. Suppose if the machine is connected to infinite bus bar, that frequency is nothing but bus bar frequency. Therefore, what ns is representing here, ns is nothing but the speed at which stator field is rotating. So I can say this is not stator speed, guys, it is stator field speed. Okay. Now, under normal steady state conditions, rotor will also rotate at synchronous speed only. We all know that synchronous machine means the speed of the rotor is equal to synchronous speed. Rotor is also rotating at synchronous speed only. That means rotor is here. Okay. If rotor is at this point, can I say rotor conductors are also at the same point? Now these three circles are representing rotor conductors. And here you can understand NR is equal to NS. This is normal steady state condition of a synchronous machine. But suppose if a load suddenly changes, let us say load is suddenly increased or load is suddenly decreased. If whenever load suddenly changes, what happens? The motor may accelerate or the motor may decelerate. It depends upon the change in load. Suppose if load suddenly increases, what happens? We all know that load torque is always an opposition torque. If opposition torque suddenly increases, what happens? The machine will decelerate. Because of that deceleration, the speed of the rotor will suddenly change. The rotor speed will suddenly change. I said load is an opposition torque. Whenever load suddenly increases, the speed of the motor will suddenly decrease. Now, rotor speed is not equal to synchronous speed. Rotor speed is less than synchronous speed. Why rotor speed is less than synchronous speed? Because machine suddenly decelerated. Why it is suddenly decelerated? Because of the opposition torque increases. That is load torque increases. Now see what happens. The moment when rotor suddenly decelerated, a relative speed is created between stator field and rotor conductors. See, stator field is at synchronous speed, rotor conductors is at this particular location. Can I say there exists a relative speed between these two now? What is the relative speed between stator field and rotor conductors? Yes, this gap, that is nothing but ns minus nr. Now, due to this relative speed, see what is going to happen. Due to the relative speed between stator field and rotor conductors, that is ns minus nr, that relative speed will induce an EMF in rotor winding. That relative speed will induce an EMF in rotor winding. This is known as commonly rotational induced EMF. And once EMF is induced in rotor winding, what will happen? This EMF will circulate a current through rotor winding. Rotor winding is a closed circuit. Suppose if it is a salient pole machine, damper winding will create this particular EMF and current. If it is a cylindrical rotor machine, the distributed rotor winding itself will have this phenomenon. And once a current is passing through rotor winding, now rotor winding is a normal winding or current carrying winding. Current carrying winding, these current carrying rotor conductors will experience a torque. According to Lorentz force equation, any current carrying conductor placed inside a magnetic field will experience a force or torque. And this torque is what we call it as damping torque. Okay, damping torque. Now what happens according to Lenz law? If you apply Lenz law, whatever damping torque is created, this is the effect here. What is the reason for damping torque? Current passing through rotor. What is the reason for current in rotor? EMF in rotor. What is the reason for EMF? Speed or relative speed? Relative speed. Relative speed between what and what? Stator field and rotor conductors. Therefore, according to Lenz law, what will happen? This damping torque will try to reduce the cause of the production here. That means whatever the damping torque is created, it will try to reduce this relative speed. How to reduce this relative speed? Very simple. To reduce this relative speed, look at this diagram. This NR should be pushed in the direction of the stator field. So what happens now? Whatever the damping torque is created, it will try to push the rotor in the direction of stator field. This is damping torque. Okay. So once the rotor is pushed in this direction, rotor will slowly accelerate and finally rotor reaches to synchronous speed. Once the rotor reaches to synchronous speed, what will happen? This relative speed becomes 0. Yes, because if ns is equal to nr, definitely relative speed is 0. then there is no EMF in rotor. Let's come back here. If relative speed is 0, no EMF in rotor, no current in rotor, no damping torque. But even though damping torque is 0, rotor will not stop here. Okay, due to mechanical inertia, rotor will further accelerate. Okay, initially damping torque is pushing the rotor slowly. Rotor will come to synchronous speed, but damping torque will not become zero. Damping torque will become 0 here, but rotor won't stop. Why? Because so far damping torque is pushing it, right? Because of that, mechanical inertia is there in the rotor. Due to that inertia, rotor will not stop here. Rotor will further accelerate. If rotor further accelerated, what will happen? Nr is more than ns. If Nr is more than ns, again relative speed is created. Again EMF will induce in rotor. Again current is created. Again damping torque is produced. This time, as Nr is more than ns, damping torque will oppose the movement of the rotor. Now rotor will decelerate and it will come below ns, next above ns, again below, again like that. This is what we call it as oscillation in rotor. And after a finite time, these oscillations will reduce gradually and finally rotor will find steady state at synchronous speed. So this is what actually is happening in hunting phenomena. I tried to explain briefly, not we are going in depth, okay, just a brief introduction. So this is hunting phenomena. And who is trying here to reduce the hunting phenomena? Yes, the current passing through rotor. Whatever the current is passing through rotor, this rotor current is helping us to create that damping torque. And can I say when current is passing through rotor winding, it creates additional copper loss in the rotor winding. Therefore, according to the given options, the most suitable option is copper loss in the rotor part. Copper loss in the rotor part. So that copper loss in the rotor part is helping us to create that damping torque, and that damping torque is helping for the rotor to reach the synchronous speed back. But it won't reach a synchronous speed directly, it will oscillate, the rotor will oscillate in and around synchronous speed, and after a finite time the rotor will finally come to steady state synchronous speed. Okay, so this is understanding the phenomena briefly. Okay, we are not going in depth. This is brief observation of hunting problem. Okay, and observation according to the options is rotor current. The rotor current is helping us to reach synchronous speed back. Okay, yes. Now read this question. Consider a system consisting of synchronous generator working at a lagging power factor, a synchronous motor working at an overexcited condition, and a directly grid connected induction generator. Consider capacitive VAR to be a source and inductive VAR to be sink of reactive power. Which of the following statements are true? That means they are asking who is acting like source of reactive power, who is acting like sink of reactive power, and how many machines are working here? 3 machines are working. The first one is synchronous generator working at lagging power factor. This is the first machine. Okay, and then we have a synchronous motor working at overexcited condition. This is the second machine. And there is a third machine also. What is that? A grid connected induction generator. This is the third machine. Okay, overall 3 machines are working there. And capacitive VAR, we know capacitor is nothing but an element which will generate reactive power, right? So whoever is generating reactive power, they are nothing but sources for reactive power. Whoever is absorbing reactive power, they are nothing but sink for the reactive power. So question is all about who is acting like source here, who is acting like sink here. Okay, 3 machines are working. So let me take a small diagram here. Okay, so imagine this is the infinite bus bar here. This is the bus bar. And 3 machines are connected to this bus bar. First one is a synchronous generator. I better write it as alternator. First machine is an alternator. Second machine is a synchronous motor. Third machine is induction generator. All are connected to same bus bar. Now what is the power factor condition of alternator? It was very clearly mentioned. Alternator is working at lagging power factor. alternator is at lagging power factor. Synchronous motor is overexcited. This is also given in the problem. Synchronous motor is overexcited. And the induction generator. Okay, we will talk about it later. Let's first discuss about synchronous machines. Now we know an alternator working at lagging power factor means which excitation? Yes, alternator lagging power factor means overexcitation. We all know that any synchronous machine which is under overexcitation, it is always generating reactive power. Any synchronous machine, that means it may be a synchronous generator or it may be a synchronous motor, overexcitation will always represent generation of reactive power. Therefore, alternator is generating reactive power. At the same time, it is clearly mentioned synchronous motor is also overexcited. Overexcitation means reactive power is generated. Therefore, both synchronous machines are generating reactive power. But coming to induction machine, we all know that irrespective of machine condition, it may be induction motoring or induction generating, an induction machine will always absorb reactive power. Because it is a singly excited machine, right? Induction machine is a singly excited machine. Rotor will not be excited, only stator will be excited. So, in order to set up the magnetic field in the air gap, induction machine will always absorb reactive power. Therefore, finally, what are the elements acting like a source for the reactive power and what are acting like a sink for the reactive power? Yes, both synchronous machines, that is generator and motor, are acting like reactive power sources and the induction machine is acting like reactive power sink. In that case, what is the correct answer here? So read the options given. Synchronous motor and synchronous generator are sources. Yes, that is perfect. And the induction generator is a sink of reactive power. Yes, first option is clearly suitable. Look at the second option. Synchronous motor, induction generator are sources. This is wrong. Induction generator is not a source. Induction generator is a sink for reactive power. See, students use it to confuse that, sir, generator means a source. Okay, generator is a source, but that is not for reactive power, that is for active power. Generator is a source for active power, but reactive power depends upon what type of machine it is, at what excitation the machine is. Okay, right. And if you look at the third statement, synchronous motor is a source, induction generator and synchronous generator are sink. Synchronous generator is not a sink. Why? Synchronous generator is currently at a lagging power factor. We know any synchronous generator at a lagging power factor means it is overexcited. Overexcited synchronous generator will always generate reactive power. So the suitable answer is option A here. Option A. This question was given in GATE 2016 and it is a 1 mark question. Easy question. Okay. All right. So let's try to answer one more question. This is GATE 2017 exam paper. Right. In a synchronous motor, question is about synchronous motor, is running at a leading power factor. Synchronous motor, leading power factor. Its excitation induced EMF, EF, is equal to terminal voltage, greater than terminal voltage, less than terminal voltage, depends upon supply voltage. These are the four options given. So point you need to understand is, it is a synchronous motor, that too at leading power factor. We all know that synchronous motor at leading power factor. At leading power factor. That means what is the excitation? Yes, synchronous motor at leading power factor means it is overexcitation. Overexcitation. Yes, overexcitation means what is the condition? Overexcited synchronous machine means EF cos delta is greater than Vt. Okay. EF cos delta greater than Vt. Don't compare EF and Vt. We have to compare EF cos delta and Vt. But in the question, we need to compare EF value and Vt value. So what you do is that take this cos delta to the right side. Therefore, EF value is greater than Vt by cos delta. And what is the range of cos delta? Suppose if delta is equal to 0, cos 0 will be equal to how much? 1. If delta is a finite value, cos of any finite angle except 0 is less than 1. So whether cos delta is equal to 1 or less than 1, 1 by cos delta will be always greater than 1 only. That means EF value will be always greater than VT irrespective of cos delta value. I repeat again, what is the range of cos delta? If delta is 0, that is no load condition, cos delta is 1. Even if cos delta is 1, EF is greater than VT. Suppose delta is a finite value, that is a loaded condition. If motor is at loaded condition, delta is a finite angle. Let's take 30 degrees or 40 degrees or any angle you take, cos of any finite angle is less than 1. 1 by less than 1 will become greater than 1. Therefore, this relation will continue to hold, EF greater than VT. So therefore, finally, what is the correct answer here? Induced EMF EF is higher than terminal voltage. Option B is correct. Okay, right. Easy question. Suppose if I modify this question slightly, what happens if a synchronous motor is at lagging power factor? Suppose if the question is given like this. Synchronous motor at lagging power factor. Synchronous motor at lagging power factor. Lagging power factor of motoring machine means what is the excitation? Under excitation. It is under excitation. When a synchronous motor is under excited, what is the condition? EF cos delta is less than VT. Yes or not? EF cos delta less than VT means what about EF? Therefore, EF will be less than VT divided by cos delta. Suppose if delta is equal to 0 degrees, let's say no load condition. No load condition means load angle delta is 0. If delta is 0 degrees, what is cos 0? 1. Then EF is less than VT. That is true. If delta is equal to 0 degrees, definitely EF less than VT. This is correct. But what if delta is not equal to 0? That means motor is connected to some load. When load is present, delta is a finite value, load angle. If delta is a finite value, we know cos of any finite angle is less than 1. Suppose if cos delta is less than 1, 1 by cos delta will become greater than 1. In that case, EF cannot be always less than VT. Okay, it depends upon various other factors like what amount of excitation we have given, what amount of load angle is given. Okay, so if delta is not equal to 0, this relation cannot continue forever. You cannot say always EF less than VT. Yes, EF may be less than VT, EF may be greater than VT also, or EF may be equal to VT also. It all depends upon cos delta value and EF value and VT value. Okay, so this is when the machine is at lagging power factor. Therefore, if the machine is lagging power factor, you can't always say EF is less than VT. EF is less than VT only when delta is equal to 0. This is compulsory true. But the other values of delta, you can't hold this relation because it may be equal to VT or less than VT or greater than VT. It depends upon EF value, VT value and delta value. Alright, so we have one more question. This is from GATE 2017 question paper. Read the problem. A 3-phase 50 Hz star connected cylindrical rotor synchronous machine is running as a motor. It is running as a motor. The machine is operated from a 6.6 kV grid and drawing a current at unity power factor. Okay, see, drawing current at unity power factor. Okay, the synchronous reactance of the motor is 30 ohm per phase. The load angle is 30 degrees. Power delivered to the motor in kilowatt is how much? Very simple question. See that? What was the data given? It was a motor, first point. It's a motoring machine. What is the supply voltage of the machine? 6.6 kV grid. Okay. And it is a star connected machine, guys. By default, given voltage is always line value. Then what will be the phase value? So the phase value is equal to 6600 divided by √3. This is the phase voltage. Next, machine is drawing a current at unity power factor. Power factor is unity, UPF. And the load angle is also given. What is the load angle given? 30 degrees. 30 degrees is the load angle. Synchronous reactance is given. Excess value is given 30 ohms. 30 ohm per phase. No information about armature resistance, so neglect armature resistance. Now we are asked to calculate what is the amount of power delivered to the motor in kilowatt. Kilowatt means active power. We need to calculate what is the active power drawn by the motor. Yes, how to answer this question? So to calculate active power drawn by the motor, I can directly use the formula. See, as the load angle delta was already there, let us try to write down active power formula in terms of load angle. Okay. So what is the formula for active power in terms of load angle? Active power is equal to 3 times of EF into VT divided by XS into sine delta. Okay. Now in this equation, delta value was already available. XS value was already available. VT value was also available. What is the only unknown to calculate active power? EF. How to calculate EF? Yes. To calculate EF, I will use the power factor information given. At what power factor machine is operating? Unity power factor. We all know that unity power factor means normal excitation. Normal excitation means, can I write down EF cos delta is equal to VT? Yes. Normal excitation. What is the condition for normal excitation? EF cos delta is equal to VT. All right or not? So from this equation, you can find out EF value. Therefore, EF is equal to VT divided by cos delta. Okay. What is VT? 6600 divided by root 3. What is delta given in the problem? 30 degrees. Isn't it? Let me check again. Yes, delta is equal to 30 degrees. So if I substitute the data here, I will get the magnitude of EF. Okay, so let me use calculator. 6600 divided by root 3, okay, by cos 30 degrees. Okay, I am getting EF is equal to 4400 volt per phase. Now, the moment I got EF value, I can easily calculate active power. Okay, you can solve it. So, now active power P is equal to 3 times of EF 4400 and what is VT? 6600 by root 3 divided by XS is given as 30 ohms into sine delta is 30 degrees. And if you complete it, you will get the answer in watt, then convert into kilowatt. Okay, so 4400 into 3 into 6600 by root 3 divided by 30 into sine 30 degrees. So I am getting 8383 watt. Okay, that means indirectly 8.38 kilowatt. Easy question. Okay, so important observation is unity power factor. As a power factor is unity, you can understand it is a normally excited machine. So EF cos delta and VT. See, the same question can be remodified. You see that in this question, current magnitude was not given, guys, right? They said drawing a current, but they did not mention the magnitude of the current. Without current magnitude, they gave you load angle value, delta. If I wanted to modify the question, what I can do? I can give you the same model. Next time, I don't give you load angle. Instead of that, I will give you current magnitude. Okay. Suppose if current magnitude is available, but load angle is not available, then you cannot use this formula because delta is unknown. Delta becomes unknown, EF also becomes unknown. If two unknowns are there, you can't find out the answer. In that case, what you can do, you can use the formula. What is the yes, you can use induced EMF formula. We have one more formula for induced EMF. What is that? Induced EMF is equal to square root of VT cos phi plus IA RA whole square plus VT sin phi plus or minus IA XS whole square. Now you can use this formula to calculate induced EMF. And once induced EMF was calculated, you can find out the answer for load angle. Okay, this time I won't ask you to calculate what is the active power drawn by the load. I will ask you to calculate load angle. First you will get EF magnitude, then you can find out load angle. But to use this formula, you must know what is the current drawn by the motor. Understand? Okay, this is another model you can expect. All right. So we have the next question. This is GATE 2018 examination, 1 mark question. And you can read the problem. In a salient pole synchronous motor, the developed reluctance power attains the maximum value when the load angle in electrical degrees is how much? The question is about reluctance torque. Reluctance torque or reluctance power, both are proportional to each other. So reluctance torque will attain maximum value at what load angle? We all know that in a salient pole synchronous machine, power will have two components, right? What is the total power equation? One will be electromagnetic component, which is EF into VT divided by XD into sine delta. Another one is reluctance component, VT square by 2 into 1 by XQ minus 1 by XD into sine 2 delta. Okay. Now the question is about reluctance torque, and reluctance torque will be proportional to reluctance power. So if reluctance power is maximum, reluctance torque will also be maximum, because in a synchronous machine, torque is directly proportional to power. And tell me, at what load angle this reluctance power will be maximum? Yes, if 2 delta is equal to 90 degrees. We know sine 90 is maximum. 2 delta will be 90 degrees if delta is equal to 45 degrees. Therefore, the answer is 45 degrees. Alright, so we have one more question. This is from GATE 2019 paper. 1 mark question. Read the problem. A 3-phase synchronous motor drawing 200 amperes from the line at unity power factor at rated load. Considering the same line voltage and load, the line current at a power factor of 0.5 leading is how much? So there are two cases here. In the first case, it is a motor, first point, synchronous motor. In the first case, machine is drawing 200 amperes at unity power factor, guys. Power factor is unity at rated load. This is the first case. In the second case, considering the same line voltage is the same, and also the load is also same. What does mean by load is the same? The active power is same. Okay, load, mechanical load is always real power. When I said load is the same, the load power remains the same. Indirectly, the active power drawn by motor remains the same. What is the line current if the power factor is changing to 0.5 leading? Okay, so that's the question all about. A very simple question. When I said the active power is the same, what is the formula for active power? Root 3 VL IL cos phi. Okay, and I said very clearly load is the same, indirectly active power is the same, line voltage is the same, that means VL is the same. Therefore, what is the relation between current and power factor? Inversely proportional. Therefore, current is inversely proportional to power factor. If current is inversely proportional to power factor, first case current divided by second case current is equal to second case power factor divided by first case power factor. What is the current in the first case? I will go back. 200 ampere. Okay, so if I substitute 200 ampere divided by second case current is equal to, what is the second case power factor? 0.5, first case power factor unity. From this, the new current will be equal to 400 ampere. Very simple, straightforward question. Okay, so the answer is 400 ampere, which is option A. Okay, so point you need to understand, I said the same load. When I said the same load, active power remains constant. Okay, so we have the next question. This is in GATE 2020 examination. Once again, the question is about excitation conditions of the machine. So see, so far we got 3 questions related to excitation conditions of the machine. So very important topic. Now see that a 3-phase cylindrical rotor synchronous generator has a synchronous reactance XS and a negligible armature resistance. The magnitude of per phase terminal voltage VA, terminal voltage, and the magnitude of per phase induced EMF EA. this is induced EMF, this is terminal voltage. Consider the following statements P and Q. What is the statement P? For any three-phase balanced leading load connected across the terminals of the synchronous generator, VA is always more than EA. This is the first statement. This is for leading power factor. For any leading power factor, VA is always more than EA. It is true or false? Second statement. For any three-phase balanced lagging load connected across the terminals of the synchronous generator, VA always less than EA. So indirectly, they gave two statements for us. Which statement is true and which statement is false? If you look at the first statement, this is for a leading power factor, and they are just asking us to compare terminal voltage and induced EMF. Generally, what is the difference between terminal voltage and induced EMF of an alternator? Is it nothing but voltage regulation? Therefore, if I consider voltage regulation curve, I can easily answer this question. Okay, let me consider voltage regulation curve of a synchronous generator. Yes, the same voltage regulation curve we will study in transformer as well. Okay, if I take voltage regulation on y-axis, positive regulation and negative voltage regulation, and if I take power factor on x-axis, lagging power factor here and leading power factor here, and what is the shape of the voltage regulation? We know this is how regulation curve will change. And if you look at the right side, guys, from here to here, this is lagging power factor. For all lagging power factor loads, can I say regulation is always a positive curve? Okay, see that? For all lagging power factor loads, regulation is a positive curve. Regulation is positive means indirectly. First of all, what is meant by voltage regulation? Voltage regulation is the change in terminal voltage from no load to full load. No load terminal voltage EF, full load terminal voltage VT. And when I said this voltage regulation is positive, voltage regulation is positive means this difference is positive. This difference is positive means EF is always greater than VT, or VT is always less than EF. Right or not? This is true if voltage regulation is positive. Voltage regulation is positive for which power factor? For all lagging power factors. You can see voltage regulation is always a positive quantity. That means look at the second statement. Second statement is for lagging power factor. So for all lagging power factors, voltage regulation is a positive quantity. Voltage regulation positive means terminal voltage is always less than EMF. This is a correct statement. That is what I proved here. See, for all positive voltage regulations, terminal voltage is less than induced EMF. This is a correct statement. So second statement is pakka true. Okay. But what about first statement? First statement, what is the power factor they considered? Let me drag down. Yes. In the first statement, the power factor is leading type. Leading type means, let's go back to the regulation curve. Leading type means, can I say left side curve? Now see that in this particular zone, when power factor is leading, yes, regulation curve can be positive. See this is a positive zone. Regulation can also be 0. This is 0 regulation point. See, y-axis is regulation. And look at all these points. These are all negative voltage regulation. So when power factor is a leading type, positive regulation is possible, 0 regulation is possible, negative regulation is also possible. Suppose if regulation is positive, VT less than EF is a true. If regulation is negative, voltage regulation, which is EF minus VT. Suppose if this is a negative regulation, what is the meaning of it? Negative regulation means this difference is negative. That indicates EF is greater than VT. Suppose if you consider 0 voltage regulation, EF is equal to VT. EF will become equal to VT. That means the point is, when power factor is a leading type, anything is possible. Anything is possible. It may be positive regulation, so VT less than EF. It may be negative regulation, Vt is greater than Ef. It may be zero regulation, Vt is equal to Ef. All three possibilities are there. That means first statement is not correct because they said Vt always more than Vt. That is not a correct statement. Always more than Vt is Ef is not a correct statement. It can be more than Ef, it can be less than Ef, it can also be equal to Ef, because all three possibilities are there. It depends upon the amount of leading power factor. Okay, so what is the correct answer now? P is compulsory true, but P is compulsory false, Q is compulsory true. Okay, so what is the correct answer? P false, Q true. Therefore, option A is satisfying the correct answer. That's all. It's about voltage regulation concept. That's it, guys. These are the questions we have in synchronous machines. That too 1 mark questions. See, the last 1 mark question in a synchronous machine came from 2020 exam. In 21, 22, 23 papers, we have 2 marks questions, no 1 mark question. Therefore, in GATE 2024 exam paper, you can expect 1 mark question from synchronous machine because we don't have in the past 3 papers. Okay. And overall, how many 1 mark questions we have? We have overall 8 1 mark questions in the past 13 years of papers. I took from 2011 to 2013. In 13 years papers, we have 8 1 mark questions. Okay, so it's almost like 3 by 4 times. So in one next lecture, I will try to discuss about the 2 marks questions that we have from GATE previous examination papers in synchronous machines subject. Okay, thanks for watching.